Hello everyone, so today I'm going to be discussing with you all the Nmr Spectra of 2-propanol. And so what I have written here is a common way to discuss the Nmr Spectra of a molecule. And keep in mind this can be used for any molecule, not just propanol. So I'm going to be going over each one of these. So to begin, the number of signals tells you the comparison of protons in a molecule compared to the other signals. So in this case, propanol has two signals, one here and one over here. And then the integral is going to tell you the number of hydrogens on each signal. The integral number is going to be the most obvious because, as you can see here, it's already included. So in this area it's going to be 1H, and in this area it's going to be 6H. And then, okay, I just realized I skipped over the position of the signal. So this is going to be the position of the signal, and this is where it's going to get very specific. This is what's going to give you away the answer, basically. So you're going to be looking for exactly where the ppm of the H is. So you're going to be looking at this bottom number and seeing where exactly the hydrogen is. Okay, and then the M for shape, this is just going to give you the multiplicity of that hydrogen. And then the number of H's on the Nmr, I'll explain how to get this once I get there because it does require a small equation. And then you're going to guess what functional group is going to be found in that area. And so, like I mentioned, propanol is going to have two signals, and I'm going to go ahead and label these A and B so that we can analyze each signal individually. So if we go ahead and begin with the A, we're going to go ahead and find the very specific ppm of this signal over here. And so by zooming in into the spectra, I'm going to conclude that this is approximately 3.6 ppm. And so I'm going to go ahead and write 3.6 over here. And then, like I mentioned, the integral is going to be the easiest one to find because it's a given. So right here, it's going to be 1H. Okay, and then now in order to find the shape, you're going to count how many spikes are in this signal. So if you want to go ahead and zoom in. So we have 1, 2, 3, 4, 5, 6, and 7 spikes. And so what this means is that the shape is going to be a septet, which means it has 7. Okay, and now in order to find the number of neighbors, we're going to use the n+1 multiplicity rule. And so here n is going to equal the number of neighbors. And so how you find this is that you're going to look at the spikes over here. So because we counted 7, we're going to do 7 minus 1, which gives you a 6. 6 is going to be your n, and 6 is going to be your number of neighbors. And so in order to find the guess, we're going to go back to the position of the signal here, 3.6 ppm, and we're going to go look at a chart that is going to be given to you whenever you're discussing spectra. Okay, so this is the chart for HNMR, and as you can see here, around 3.6 ppm is going to be right about here. And as you can see, a lot of these are attached to oxygen, so we're going to predict that whichever molecule is here, its neighbor is going to be an oxygen. Because we know that the Nmr spectra that we're looking at belongs to propanol, the only option we have basically is for this signal to belong to the oxygen group that is found in propanol. Okay, and so now we're going to do the same thing but with our B signal. So around here we're going to say that this is like a 1.2 or a 1.1 ppm. We're going to write that down over here. And then again, the integral is always going to be given, so here it's going to be 6h. And then I don't know if I mentioned it or not, but the integral is going to tell you the number of hydrogens the integral or the signal is going to be bound to. Because this has 2 spikes, this is going to be considered a doublet. And then again, we're going to do the same thing that we did to find the number of hydrogens for A. So we're going to do 2 because it's a doublet minus 1, which gives you 1. So that means there's going to be one neighbor, or there's going to be one hydrogen as a neighbor. And so a common rule in NMR is that anytime that you have a doublet, it's most likely going to be a CH group. And so even though the doublet gives it away that it's a CH group, we're going to go back to the literature spectra and see. Okay, so right here at 1.1 approximately, we see the alkanes family. So we're going to see a carbon attached to a carbon attached to a hydrogen. So we're going to go ahead and go back and write that. So right here I'm writing carbon attached to an oxygen, and then so slowly we're gonna start figuring out which functional groups are gonna be in the molecule that the NMR spectra belongs to. And so drawing partial structures is gonna be your best friend when figuring it out, because it's gonna help you determine which molecule you're looking at. Okay, and then something I also forgot to mention was that the 3.6 ppm gives it away that it's an oxygen, or that it's a alcohol, because at 3.6 ppm there's going to be a lot of deshielding, and deshielding comes with electronegativity, and because oxygen is electronegative, it's going to have more deshielding than the signal P. And so in order to draw the final structure, we're going to start off by drawing out the alcohol group that's in here, and then we see that the carbon is going to be attached to the carbon, and then we're also going to miss the two other alkane structures. So we're going to draw one here and one on the other side, like that. And then because the number of hydrogens adds up to 7, we need the number of hydrogens in the final molecule to add up to 7. So we're basically just going to add the remaining hydrogens that we need. And so what that's going to look like is you're going to add hydrogens to the remaining carbons. And so when you finish that, you're going to have 1, 2, 3, 4, 5, 6, 7 hydrogens, not including the hydrogen in the alcohol. So you should have 7 hydrogens total. And basically that is the a brief discussion of 2-propanol. And now what you can do is take this molecule and make sure that all the ppm spikes in the NMR correspond to the molecule and its structure. Okay, and so now we're going to move on to discuss the Nmr of Aspirin, which is a painkiller. And so again, like in the other example, we're going to have this signal, which is telling you which peak you're addressing. So whether it's A, B, and then over here it's zoomed in, as you can see. So this is going to be B, C, D, and then this is going to be E. So I'm going to go ahead and write out B, C, D, and E. These are all the signals that we're going to be looking at. And so then after that, we're going to look at each of the positions for each signal, which is the ppm value for that specific signal. And then the integral, which is a given in the other example, but in this case, we're just going to ignore it. So we're going to go ahead and we're just going to go ahead and cross those out because these are not given. And don't worry, we're still going to be able to get the same structure because we're going to rely a lot on the position and on the ppm values. Then you're going to get the M, which is the shape, and then the number of hydrogens, which you get from the multiplicity. And then you're going to go ahead and guess a functional group. So let's go ahead and begin with A. Okay, so A, as you could see here, has a ppm value of 11. We crossed out the integral, so now we're going to do the shape. The shape of this peak is a singlet. So now we're going to go ahead and write singlet over here. And because it's a singlet, it tells us that it has 0 hydrogens. And again, keep in mind that this is going to be the neighbor. So the neighbor has 0 hydrogens attached. And so now if you go to the literature spectra of the vibrational frequencies over here for NMR, we are going to see that around 11 ppm, we have this carboxylic acids. So I'm going to go ahead and write carboxylic acid. And I'm going to do this just to have a picture. Okay, so now moving on to B. For here, I'm going to say B has approximately 8.2 ppm value. And so now we're going to go ahead and count the peaks. So remember, this is a zoomed in version of these 3 peaks right here. So this is going to act as B. So it's going to be 1. Oh, give me a sec. 1, 2, 3, 4, 5, 6. So because it has 6 peaks, this is going to be called a sextet. And because it's a sextet, we use the multiplicity rule. So it gives us 5 H's for the neighbor. And so now if we go at the NMR frequency table, this is going to be approximately 8.12, how we said. And we can see that the alkenes and the aromatic compounds both align with that value. So we're going to go ahead and write both of those over here. So this is alkenes and aromatic for B. Now moving on to C. C over here is really close to the signal of B. So we're going to say that C has a 7.9 ppm value. And then again, there's no integral. And then for the multiplicity, we're going to go ahead and count the number of peaks. And then remember that this is going to be C. So it's going to be 1, 2, 3, 4, 5, and 6. So we're going to have another sextet. And another 5 hydrogen molecule next to it, or 5 hydrogen atom next to it. And so because 7.9 is so close to 8.2, we're gonna go ahead and say that it's gonna be for alkenes or aromatic because they're so close, and we don't have to go back to look at the table. But just in case you guys did want to, here's the table, and it's around the same area as you can see. And then the same thing is going to happen with D. So as you guys can see here, I know it's very squished, but we're going to say that D has a ppm value of 7.8 because it's right before C. So we're going to say 7.8 ppm for D. Again, this is going to be another sextet with another 5 hydrogens attached to the neighbor. And then it's going to be the same thing, alkenes and aromatic. And the reason why we are seeing this is because of the multiplicity of doublet of doublets. So this is going to pop up, which is why we see 3 signals very, very close to each other here. So that's the doublet of doublets rule. And remember that doublet of doublets happen because of coupling. And then last but not least, we have this singlet over here for E. So E is going to have a ppm value of 2.2, let's say. So we go down here and fill out 2.2 ppm. As mentioned, this is going to be a single, which means it's going to have 0 oxygen or 0 hydrogens next to it. And then if we go at the frequency table for NMR, we see, give me a sec, we see that around 2, around the value of E, we're going to have alcohols. So this is most likely going to be our alcohol functional group. So we're going to begin by drawing out the molecule that's for sure going to be found. And that's going to be a benzene ring, an aromatic compound. We're going to go ahead and connect this to an O, which will then be connected to a carboxylic acid. And then we're going to have we're going to have a double bonded O over here. And then this is going to be bond to the alcohol. And I reached my time limit, so that's the discussion for aspirin. If you have any questions, please go ahead and let me know. Thank you.